the binomial distribution equation. So that way you guys understand when the calculator is calculating a binomial distribution, what it's exactly doing, okay? All right, so we have a binomial distribution, right? So if x is binomially distributed, right? Now remember this value here represents our number of trials. So number of trials for the question. And then this other value here is basically the probability of success, all right, of whatever we've defined as capital X. Okay. Okay, so let's take a look at the expansion form of a binomial distribution, right? So let's say we've defined capital X as some sort of random variable, okay? And n is the number of trials, right? And p is the probability of success. Now, when you set up a binomial, so let's say we have the probability of capital X is equal to, all right, some x value, right, some number. So when you set up the binomial distribution, when you expand it out, right, all right, so this is going to tie into when we did binomial theorem earlier, right, in topic 1. So the number of trials always goes here, okay? Now this represents the probability of success. So this represents the probability of success. All right, so in this case, it'll be p, right? Because remember, p was the probability of success, all right, for the variable x. So the probability of failure would be 1 minus p. So this over here represents failure, right? You don't get what you were looking for, all right? Now, whatever the exponent of success is, right? So whatever this exponent is, all right, we'll just say it's x. So this would be x here. And then these two exponents always have to add up to the number of trials. So this would be n minus whatever x is. Okay, so whenever you're expanding a binomial distribution problem, you have to keep in mind this kind of format here, right? I'll use this example down here so you guys get a better idea of kind of what everything means. It's kind of hard to comprehend kind of maybe just from this equation, right? So let's take a look at this example down here. So it says 86% of members in the teachers union is in favor of a change in work hours, right? A random sample of 8 members is taken. Find the probability that. So the first thing we need to do is we have to recognize this is a possible binomial distribution question, okay? So we think about our 4 requirements, right? So first of all, if we define capital X, right? Basically capital X represents they're in favor of a change in work hours, right? So they're in favor of a change in work hours. Now, it says the probability of this, right, them being in favor is 86%. So we know the probability of success of this, so the probability of this is 86%, right? And the probabilities don't change, and then they're saying there's 8 members, right? A survey, a random sample of 8 members, so that's your number of trials. So if we were to set this up, our binomial distribution parameters, right? So since this meets the 4 requirements, right? We have the number of trials is 8 because it's a sample of 8 members. The probability of success, right? Success in this case is defined by capital X in favor of change. So it says 86% of members are in favor of change. So that would be 0.86, right? So these are the parameters for our binomial distribution, okay? So I'm going to use this now to answer these questions. So let's take a look at A. It says, find the probability that 2 members are in favor of a change in work hours. So basically we're trying to find the probability. So exactly 2 members. So X would equal 2. Okay? Now, so to work this out, or if we actually expand this, right? I just want to make sure you understand what this means. So if we were to actually expand this, so if X is equal to 2, that means that if we set up our kind of 3 parentheses. So this here, number of trials is 8. So that always goes here, right? Now the probability of success, that's 0.86. And this, all right, so remember this represents the probability of success. Oops, too many S's. So if the probability of success is 0.86, this would be 1 minus 0.86, right? Oops, 0.86. So, or you can just mentally work that out and put 0.16. Oh, sorry, 0.14, right? Now, if x is equal to 2, we want success, right? This exponent has to be 2 because we're trying to find x is equal to 2, right? Now, if this is 2, this exponent has to be 6 because these two always have to add up to the number of trials, okay? Now, it doesn't really make a difference. You could put 2 here or 6. It's not going to make a difference. If you actually calculate this right here, this combination, it's going to give you the same value if you put a 2 or a 6 here, right? Similar to when we were doing binomial theorem, right? So if we actually work all this out by hand, right? So over here, remember this represents failure. If we actually work this out by hand, right? If we just punch in these numbers in the calculator, right? It'll give us our solution. So I could just show you real quick. So let me just go to probability, combination. So we need to find 8 choose 2 first. So 8 comma 2. So that gives us 28. So we know that value is 28. So basically we have 28 times 0.86 to the second power, and this would be 0.14 to the sixth power, right? And then if we just calculate that, so we have 28 times 0.86 exponent 2 times, and then 0.14 exponent 6, right? So we get our answer 0.000159, right? So 0.000159. Okay, so now using the calculator, we can do the exact same thing, just so you see, right? If we go to menu, probability distribution, all right, we're going to use a PDF because it's x equals, so PDF. So number of trials, we have 8 members. Probability of success, 0.86. X is equal to 2 because we want 2 people in favor of change. So you notice we get the same exact answer, okay? So when you use a calculator to get this answer, it's important for you to understand what this answer actually represents. If you were to actually expand out using the binomial distribution equation, this is what you are calculating. So this is important to know because the harder type questions that are binomial distribution questions, they will require you to be able to expand out this way. Okay, so that's why it's important to understand, okay, how to actually use and expand out the binomial distribution equation. Okay, let's take a look at part B here. So let me do part B. All right, so part B. The probability at least 6 members are in favor of change. So the probability of at least 6. So we're finding the probability of x is greater than or equal to 6, right? So first of all, when you see this greater than or equal to 6, so that means it can be 6 members, 7 members, or 8. Because remember, there's 8 members, 8 number of trials. So when you expand this out, you have to understand that, okay, we're trying to find out the probability when x is equal to 6, right, plus the probability when x is equal to 7, right, plus the probability when x is equal to 8, right? So when we expand this out, this would be, so this is 0.86 right here, 0.86, this would be 0.14, right? This is still going to be 8 because 8 number of trials. So this is going to have to be 6 because x is equal to 6, right? So we could put a 6 here. So this has to be 2 because these have to add up to equal this. Plus, so we have this expansion over here. Same thing. We have 8.86, 0.86, 0.14. This is going to have to be 7. This is 7 here. This will be 1 plus. And this would be 8.86, 0.14. This would be 8 here. This would be 0. and then you can put 8 here or 0. It doesn't make a difference. All right. So if you were to actually expand, right, this out by hand, right, the probability of x is greater than or equal to 6, you have to understand this means x can be 6, 7, or 8. So when you're expanding this out, we have this representing x is equal to 6, this representing x is equal to 7, this representing x is equal to 8. And if you were to actually calculate all this in the calculator, right, it'll give you the same thing as if you use just the binomial distribution function in the calculator. So if I actually use binomial distribution, right, in the calculator, I'll go to distribution. Right, this time it's going to be a CDF, binomial CDF, because we have an inequality, right? So the number of trials is still 8. Success probability is 0.86. The lower bound, so what's the lowest number x can be? So greater than or equal to 6 means the lowest number x can be is 6. What's the highest? The highest number is 8 because there's only 8 number of trials, right? 8 people. We click that in, we get 0.91092. So this is going to be approximately 0.91092, right? So if you were to actually calculate all of this and just, punch in the numbers in the calculator, you will get the same exact answer as using binomial CDF, right? And putting in, all right, these parameters right here, right? Binomial CDF, we had, right, 8 number of trials, success was 0.86, lower bound was 6, upper bound was 8, and we would get the same exact answer right here. Okay, so it's very important, like I said, it's very important for you to understand that, yeah, some of the easier questions, you can just put this in the calculator and get the answer. But the more difficult questions, you have to understand what's really happening when you get this answer. What does this represent? This represents the probability of getting a 6, 7, or 8, and all these individually are being added together to get this final answer. Because the more challenging binomial distribution questions by IB will require you to understand this knowledge here, right, in order to successfully do those questions correctly. Okay? Okay, and one last thing I wanted to mention, just to make sure it's clear to everybody, the difference between binomial PDF and CDF. So you want to use binomial PDF anytime you're calculating a probability where x is equal to some number. Okay, so anytime it's a binomial distribution type question and you're calculating a probability where x is equal to any number, you use binomial PDF. You want to use binomial CDF anytime you have an inequality, right? So for example, you're trying to calculate the probability x is greater than or equal to some number, right? You could have the equal, you could not, it doesn't really make a difference. But anytime you have any sort of inequality, all right, you use binomial CDF. Okay?